With hypercalcemia, hyper means over and calc refers to calcium, and emia refers to the blood. So hypercalcemia means higher than normal calcium levels in the blood, generally over 10.5 milligrams per deciliter. Now, calcium exists as an ion with a double positive charge, Ca2+, and it's the most abundant metal in the human body. So I know what you're thinking. Yeah, we're all pretty much cyborgs. Anyways, about 99% of that calcium is in our bones in the form of calcium phosphate, also called hydroxyapatite. The last 1% is split so that the majority, about 0.99%, is extracellular, which means in the blood and in the interstitial space between cells, whereas 0.01% is intracellular, or inside cells. High levels of intracellular calcium causes cells to die. In fact, that's exactly what happens during apoptosis, also known as programmed cell death. For that reason, cells end up using a ton of energy just to keep their intracellular calcium levels low. Now, calcium gets into the cell through two types of channels, or cell doors, within the cell membrane. The first type are ligand-gated channels, which are what most cells use to let calcium in, and are primarily controlled by hormones or neurotransmitters. The second type are voltage-gated channels, which are mostly found in muscle and nerve cells and are primarily controlled by changes in the electrical membrane potential. So calcium flows in through these channels, and to prevent calcium levels from getting too high, cells kick excess calcium right back out with ATP-dependent calcium pumps, as well as sodium-calcium exchangers. In addition, most of the intracellular calcium is stored within organelles like the mitochondria and the smooth endoplasmic reticulum, and is released selectively just when it's needed. Now, the majority of the extracellular calcium, the calcium in the blood and the interstitium, is split almost equally between two groups: calcium that's diffusible and calcium that's not diffusible. Diffusible calcium is separated into two subcategories: free ionized calcium, which is involved in all sorts of cellular processes like neuronal action potentials, contraction of skeletal, smooth, and cardiac muscle, hormone secretion, and blood coagulation, all of which are tightly regulated by enzymes and hormones. The other category is complex calcium, which is where the positively charged calcium is ionically linked to tiny negatively charged molecules, like oxalate, which is a small anion that's normally found in our blood in small amounts. The complex calcium forms a molecule that's electrically neutral, but unlike free ionized calcium, it's not useful for cellular processes. Both of these are called diffusible because they're small enough to diffuse across cell membranes. Finally, though, there's non-diffusible calcium, which is bound to negatively charged proteins like albumin, and the resulting protein-calcium complex is too large and charged to cross membranes, leaving this calcium also uninvolved in cellular processes. When the body's levels of extracellular calcium change, it's detected by a surface receptor in parathyroid cells called the calcium sensing receptor. This affects the amount of parathyroid hormone that gets released by the parathyroid gland. The parathyroid hormone gets the bones to release calcium and gets the kidneys to reabsorb more calcium so it's not lost in the urine, as well as synthesize calcitriol, also known as active vitamin D. Active vitamin D then goes on to cause the gastrointestinal tract to increase calcium absorption. Altogether, these effects help to keep the extracellular levels of calcium within a very narrow range, between 8.5 to 10 milligrams per deciliter. Sometimes, though, total calcium levels in the blood, which includes diffusible and non-diffusible, can vary a bit, depending on the blood's pH and protein levels. This happens because albumin has acidic amino acids, like glutamate and aspartate, and these have carboxyl groups that are in the form of COO- or COOH. Overall, the balance of COO- and COOH changes based on the pH of the blood. Now, when there's a low blood pH, or acidosis, there are lots of protons, or H+ ions, floating around, and a lot of those COO- groups pick up a proton and become COOH. More COOH groups means that albumin generally becomes more positively charged. And since calcium's positively charged, these two repel each other. And this decreases bound calcium and increases the proportion of free ionized calcium in the blood. So as more protons bind albumin, more free ionized calcium builds up in the blood. And so even though total levels of calcium are the same, there's less bound calcium and more ionized calcium, which remember is important for cellular processes, meaning that this can lead to symptoms of hypercalcemia. Also, though, any condition that results in hyperalbuminemia or high albumin levels causes there to be a higher concentration of protein-bound calcium, while free ionized calcium concentrations stay essentially the same due to hormonal regulation. This is therefore called false hypercalcemia or pseudo-hypercalcemia, since the concentration of bound calcium increases, but the concentration of free ionized calcium stays the same. Even though this is rare, it can happen in people with dehydration, where albumin gets really concentrated. Now, true hypercalcemia might be caused by increased osteoclastic bone resorption, which is actually the most common cause. And this is where osteoclasts, which are little bone-eating cells, frantically break down the bone and release calcium into the blood. This might happen when the parathyroid gland becomes overgrown and releases more parathyroid hormone. Another well-known cause of hypercalcemia are malignant tumors, some of which secrete parathyroid hormone-related protein, or PTHrP, a hormone that mimics the effect of parathyroid hormone, which stimulates the osteoclasts. Alongside these osteoclast cells, there are also osteoblast cells, which are bone-building cells, and some tumors cause osteoblasts to die off. Overstimulated osteoclasts without enough osteoblasts can result in lytic bone lesions, which are commonly seen in some malignancies. Another cause of hypercalcemia is excess vitamin D, either through the diet or through supplements, which can cause there to be too much calcium absorbed in the gut. Finally, there are some medications, like thiazide diuretics, which increases calcium reabsorption in the distal tubule of the kidney, which contributes to hypercalcemia. High levels of ionized calcium affect a variety of cellular processes, in particular electrically active neurons. Normally, calcium ions stabilize the resting state of the sodium channels, which prevents them from spontaneously opening and letting sodium ions enter the cell. With high levels of extracellular calcium, voltage-gated sodium channels are less likely to open up, which makes it harder to reach depolarization and makes the neuron less excitable. And this is what causes slower or absent reflexes, which is a classic symptom of hypercalcemia. The sluggish firing of neurons also leads to slower muscle contraction, which causes constipation and generalized muscle weakness. In the central nervous system, hypercalcemia causes confusion, hallucinations, and stupor. In most cases, when there's too much calcium in the blood, the kidneys try to dump it into the urine, causing hypercalciuria, or excess calcium in the urine. Hypercalciuria leads to a loss of excess fluid in the kidneys, causing an individual to get dehydrated. And the combination of hypercalciuria and dehydration can lead to calcium oxalate kidney stones. Hypercalcemia is diagnosed based on high levels of calcium in the blood, generally above 10.5 milligrams per deciliter. An electrocardiogram might show changes like bradycardia, AV block, shortening of the QT interval, and sometimes in the precordial leads the appearance of an Osborn wave. To identify the cause, lab tests are typically done, looking at parathyroid hormone, vitamin D, albumin, phosphorus, and magnesium levels. In hypercalcemia, the main goal is to lower calcium levels using medications that reduce calcium in the blood. One approach is to increase urinary excretion of calcium, which can be done by rehydrating an individual, which causes more calcium to get filtered out. In addition, loop diuretics can be helpful because they inhibit calcium reabsorption in the loop of Henle, leaving calcium in the lumen of the nephron to get excreted. Another approach is to increase gastrointestinal excretion by using glucocorticoids to decrease intestinal calcium absorption, which allows it to instead simply pass through the gut without getting absorbed. Finally, you can prevent bone resorption by using biphosphonates or calcitonin to inhibit osteoclasts. Alright, as a quick recap, hypercalcemia describes a high concentration of free ionized calcium in the blood, which most commonly results from excess parathyroid hormone, as well as malignancies. High calcium levels cause excitable cells to be less excitable, which results in slow reflexes, muscle weakness, and constipation. What's going on, guys? Thanks for watching. Happy Friday. Well, it's Friday for me, so happy Friday to me. Hope you liked that video. It was really long, and expect a second part called hypocalcemia to come out as well. So be on the lookout for that one. Special thanks goes to Maria for writing the script, as well as Rishi for editing the script. I did the illustration and the voiceover, and then also huge special thanks to Yifan for editing the video. I went back and forth with him for a long time, and so huge thank you for putting up with my edits. Other than that, you guys can always support us on Patreon or subscribe to our channel and follow us on social media. All right, guys. Bye.